Assalamu alaikum and good day. The next module is on the material balance for a single unit. Here we are going to solve material balance for a process. At the end of this module, for a non-reactive system, you'll be able to describe technique to perform material balance calculation in a single unit process. You'll be also able to use drawn and label flowchart to determine whether the given problem has sufficient information prior to solving it. Lastly, you'll be able to apply the general procedure in solving the material balance calculation for any non-reactive single unit process. Even though you are very good with math, remember you have to perform material balance calculation systematically. Always draw the flowchart and check your units consistently. Remember, only variables that have similar units can be added or subtracted. You can use this prepared checklist while doing your material balance calculation, either for a single unit process or multiple units process. They will be your handy tools to check whether you are in the right track. Okay, let's look into our business. Try the following problem. Let us try this one. You're given a process in which benzene is mixed with toluene in a mixer. The benzene is fed at a rate of 3 kg per minute and the toluene is added at a rate of 1 kg per minute. You are required to calculate the overall flow rate of the mixture and to calculate the composition of benzene and toluene in the mixture. Let us see. Our keywords here are mixer, benzene, and toluene. Underline all those keywords. Before proceed with the material balance calculation, the first thing that we have to do is draw the flowchart. A mixer must have at least 2 inlet streams and at least 1 outlet stream. In general, we can draw a block diagram for a mixer as shown in this figure. Next, recall that a mixer has 2 inlets and 1 outlet streams. What are we going to do next is label the known streams or variables from the described process description and put it into the block diagram. Here, benzene is flowing in through stream number 1 at 3 kg per minute. Toluene is flowing in at 1 kg per minute in stream number 2. For stream number 3, we have yet to identify the values. Next, we are going to replace the variables on the stream and label the unknown streams. For stream number 3, we are going to denote the outlet stream as m dot for the flow rates. And since the compositions are interdependent, so we can choose one variable as x and the composition of the other as 1 minus x. Here we are going to have x kilogram of benzene per kilogram of mixture and respectively 1 minus x kilogram of toluene per kilogram of mixture. Once we label all the unknown variables, let us revisit the problem statement. We were required to determine the m dot, which is the total flow rate of the mixture in stream number 3. And we have to calculate the composition of all compounds in the mixture. Remember that mass fraction is an interdependent relationship, which means if we are able to find a value for one component, then we will be able to find a value for other components in the mixture. So, if we have x kilogram of benzene per kilogram of mixture, then the mass fraction of toluene will be 1 minus x kilogram of toluene per kilogram of mixture. Let us also check all the units involved in the calculation. Flow rate should have a unit of kilogram per minute, and mass fraction has a unit of kilogram of compound per kilogram of mixture. For non-reacting processes, the material balance takes the form of input is equals to output. The maximum number of independent equations that can be derived by writing balances on a non-reactive system equals the number of chemical species in the input and output stream. We should write balances first that involve the fewest unknown variables to reduce complex. So now, let us set up the overall equation for the process. Remember, input is equals to output for a non-reactive process. So our input are stream number 1 and stream number 2, and our output is stream number 3. Replace the terms with the known and unknown variables set previously. So we have 3 kg per minute of benzene added with 1 kg per minute of toluene is equal to m dot kilogram per minute of mixture. Next, we are setting up the equations for each component. Since we have only 2 components, we are going to set up only 2 equations for the components. We will go first with benzene. The inlet stream is 3 kg of benzene per minute. The outlet stream should have similar mass flow rate of benzene. So we have unknown, which are m dot of the total mixture, and x is the mass fraction of benzene in the mixture. Cancel out the units, we will be getting similar final units in kilogram of benzene per minute. Here we have 2 unknowns, which are m dot and x. You can set up similar equation for toluene. However, this is not an independent equation since both benzene and toluene are interdependent in terms of their mass fraction in the mixture. This equation cannot be used in the degree of freedom analysis. You can use this equation to check the truthiness of your calculation only. Let us proceed with the degree of freedom analysis of the process. The number of unknown for the process that we have are 2, which are m dot and x. Number of independent equations are also 2, which is actually the overall equations and the composition equation. Thus, the number of degree of freedom is equals to number of unknown minus number of independent equation. So here we have 2 minus 2 is equals to 0. So the problem is solvable. If they are in any cases in such that your degree of freedom is greater than 0, you might have stated more unknown, and if the degree of freedoms is less than 0, you might have over-specified your problems or your flowchart might be incomplete. So you have to go back and relook at the flowchart that you had actually drawn. The last bit will be solving the problem. Recall our equation 1 on the overall balance. Putting in all the values, we are able to solve m dot to be equals to 4.0 kilogram per minute. Then we are going to plug in the value for m dot into equation 2, and by manipulating the algebra, then we are going to get x equals to 0.75 kilogram of benzene per kilogram of mixture. This ends this module. Please refer to the module 2 for the next section.